In the field of artificial intelligence, an interesting phenomenon is humans invest different amounts of thinking time to solve problems depending on their difficulty, and sometimes they can even arrive at an answer without writing down the intermediate steps. Today, I want to share with you a new study from a research team at the University of Maryland and other institutions, which proposes a language model architecture capable of simulating this deep thinking process. This model, named Huginn, adopts the method of recurrent depth, enabling the model to reason in a continuous latent space. Compared to the current mainstream large language models, this method may open up new development directions for AI's reasoning capabilities. Traditional language models typically need to convert the thinking process into text when performing reasoning, just like we have to write down every calculation step when solving math problems. The Huginn model adopts a completely new approach. It can think directly in the latent space. This latent space is a high-dimensional mathematical space, capable of encoding complex concepts and relationships as continuous numerical vectors, rather than discrete text symbols. This approach has three main advantages. Information expression is more compact. As a single vector can contain a large amount of information, computation is more flexible, allowing for direct, continuous mathematical operations. The reasoning process is more natural, without the need to convert every thinking step into text. Additionally, compared to the currently popular chain of thought method, Huginn's new architecture demonstrates unique advantages. Firstly, it does not require special training data. Traditional chain of thought methods rely on a large number of training samples with detailed reasoning steps, while Huginn can directly use ordinary pre-trained data. Secondly, it can use a smaller context window because it does not need to store textual descriptions of intermediate reasoning steps, thus utilizing memory space more efficiently. Most importantly, this method may be closer to the actual way humans think. When solving problems, we often can directly arrive at the answer without necessarily being able to accurately describe the entire thought process in words. Moreover, the model has a notable feature of adaptability. For simple questions, such as open book QA, the model can quickly converge to an answer. While for more complex problems, such as GSM 8K math problems, the model will automatically increase computational depth to enhance performance. So, how is this innovative architecture achieved? The specific implementation of this method includes three key components: the preprocessing module, prelude, the recurrent module, recurrent block, and the decoding module, coda. First, the preprocessing module converts the input text into vector representations in the latent space. This process is similar to translating human language into a mathematical language, enabling computers to process it more effectively. Next, the core part of the model, the loop module, starts working. This module can be seen as a process of repeated thinking. It receives the initial latent representation and then updates and refines this representation multiple times through the recurrent unit. Each loop produces a new hidden state, which contains the model's understanding and reasoning results. The model automatically determines how many loops are needed based on the complexity of the task. Simple tasks may only require a few loops to arrive at an answer, while complex problems may require more loops to achieve satisfactory results. Finally, the decoding module converts the final latent state back into a human-understandable output. This is like translating the computer's thinking results back into human language. Throughout the process, the model's operations in the latent space are continuous, eliminating the need to convert each reasoning step into text as in traditional methods, making computation more efficient and natural. In the specific experiment, the research team used a model architecture with 3.5 billion parameters, 3.5B, and trained it on approximately 800 billion tokens of data that in multiple benchmark tests. This relatively small model demonstrated impressive performance. On the OpenBook QA task, it achieved good results with only 1 to 2 loop iterations, while in the more challenging GSM 8K mathematical reasoning task, by increasing the loop depth to 4 to 5 times, the model was able to gradually improve its problem-solving accuracy. This level of performance is comparable to some traditional models with 50 billion parameters, 50B, indicating that this method may have significant advantages in computational efficiency and parameter utilization. It should be noted that this method is still in its early stages. Although it performs well on certain tasks, Its generalization performance and stability require further research and validation. Additionally, since the model's inference process occurs in the latent space, this may pose challenges in terms of interpretability. This study provides new insights into the architectural design of language models that be why reasoning in the latent space. It may help us build AI systems that are closer to human cognition. As research progresses, we may see more innovative applications based on this approach.